Welcome back. We finished the section on binary integers and now we're going to have 2 weeks on a new topic, which is how we represent fractions in binary. And the first lesson is about fixed point numbers. So in this lesson we'll learn what the binary point is. We'll learn to convert binary fractions into decimal numbers and to convert decimal fractions into binary numbers. And we'll think about the trade-off that there is between the precision and range of numbers that we can represent. Let's think for a second about how the point works in a decimal number. The decimal point marks where the position values change from being whole numbers to being fractions, and each fraction is 1/10 the size of the previous one. So let's see how we would write 7 1/4. We would write 7 in the ones column, 2 in the tens column, tenths column, and 5 in the hundredths column. 7.25 is 7 1/4. The binary point works in exactly the same way. It's just that the numbers go down to a half, a quarter, an eighth, a 16th, and so on. So if we were to write 7 1/4 in binary, it would look like this. 111 is 7.01. That means and 1/4. So the binary position values to the right of the binary point are half, quarter, eighth, and a 16th. The decimal values look a bit complicated. 0.5, 0.25, 0.125, 0.0625. You're just halving the number each time, and using decimals can make it easier to do adding up later, but you can use either. If we see a binary number with a binary point in it, we put it into a binary grid as before and add up the values of every column that contains a 1. But this time the column values are on the right are different than what we've seen before. So can you do this one? I'm about to show you the answer, but can you work it out in your head? It's 8 plus 4 plus 1 plus 0.25 plus 0.125 plus, which equals 13.375. So here's a test. I'm going to suggest that you stop the lesson now, pause the video, and just do these on paper, because you're going to have to do them on paper in the exam. So you should be able to work out the decimal value of each one of those binary numbers. As you can see, it doesn't go up any further than the position values that we've already learned. Okay, so I'll give you a pause now and then I'll continue with the answers. So here are the answers. Did you get them? If you didn't, please go back a couple of slides and find out what you did wrong and try again, because you need to be able to do these pretty reliably. And obviously, if we can convert binary to decimal, we also want to be able to convert decimal to binary. And we do it just the same as we did with integers. We create the grid of position values, subtract them until we get down to 0, and put 1 below every value that you use. So obviously we can't subtract 8 or 4. We can subtract 2. That gives us 0.3125. Can't subtract 1 or 0.5. Can subtract 0.25. And that leaves us with 0.0625 left. So the answer is 10.0101. Of course, sometimes you'll have to get to smaller and smaller fractions to try to get to 0, and sometimes you won't actually be able to get to 0, and so you might have to accept a certain amount of rounding error. Okay, but there won't be any rounding errors or problems with these questions. I've made them so that you can exactly work these out as binary numbers. So convert these 5 decimal numbers into binary, and I'll pause the video and do it on paper. I'm going to show you the answers in a minute, and it's really important that you can do these on your own. These are the answers. So once again, check that you've got them right. If you still haven't quite got the knack of it, go back and have a bit more, have another look at those instructions and try again. A question that students often ask me, and I think quite rightly, is how does the computer know where the dot is? Obviously, when I do this in the lesson, I just draw a great big blob on the table to show you where it is. Obviously, there isn't a blob like that inside the computer. There are just different position values. So how does the computer know where the point is? Or let's put it another way, how does it know what the position values of the number, of the different bits in the number are? There's a number of different ways. I mean, some processors are built so that they always use the same position values throughout their memory. In most cases, that isn't the case. Different software will set things up differently. So some software might only process integers, other software might allow it to 2 binary places. It's up to the person who designs the software, really. And that's very comparable to the difference between sine and magnitude or 2's complement. You can store minus numbers in 2 different ways, and the processor might be set up to only use one of those kinds, or more likely, different software uses the processor, uses the RAM in whatever way suits the software. So we've got to understand all of these different methods because any of them might apply in any particular case. Of course, it's not perfect. Some fractions can't be expressed using point notation, it can't be expressed exactly. And we find this in decimal as well as in binary. So for instance, a third, which is a really common fraction, just can't be expressed exactly using decimal places. Or 2/3 can't. I don't think a seventh can. Anyway, I'm not going to go into them all, but there's a lot of fractions that you can't do precisely as decimals, and it's the same with binary fractions as well. So you might have to round or truncate and lose some of the precision. There isn't an easy solution to this problem. It's inherent in the nature of mathematics. However, when we're deciding how to use the bits that we've got in our memory locations, we've got a trade-off between precision and range. So if you choose range, we might not be able to do very small fractions, but we can represent quite large integers. Or we could decide to be very, very precise and use our position values for very minute fractions, but we wouldn't be able to represent big numbers. So obviously we've only got 1 byte to play with. In real life, a program will have far more than 1 byte of memory to use, but nevertheless this trade-off will have to be made at some point. So here's an example of using a byte to maximize the range. So where's the binary point in this? And what are the smallest and largest numbers you can represent? Well, the binary point is at the very far right before the number 1. The smallest number you can represent is 0. And the largest number you can represent is 255. In this case, you won't have to memorize all numbers like that, but it's just done by halving the number each time. But where's the binary point? It's right off to the left. And the smallest number you can represent, well, apart from 0, is 0.003906. And the largest number is just under 1. It's basically 1 minus that tiny fraction, that number. And here's a compromise version. The binary point's right in the middle. The smallest number you can represent is the most precise fraction is 0.0625, and the largest is just under 16. I'll write that down. Just under 16 is the biggest number you can represent. So all these examples that we've looked at are examples of fixed point numbers. That is the position of the position of the binary point has been set in advance, and all the bytes in a block of memory or whatever would have the same position values, or we could say they have the binary point in the same place in the byte. And that means that you're stuck with a particular amount of range or precision that's been decided in advance. And if you want to store a number that's too big or too precise, then you might get overflow or underflow. So we'll look at solutions to that problem in the next lesson. It's ages since I've set you a programming challenge, so I thought this would be a good opportunity to polish up those Python skills. So write a program to convert between binary and decimal fractions. Use the fixed point system. You can decide. I suggest you use that one we've just looked at, where the point's in the middle, and output a message if you get overflow or underflow, so you lose some precision or you can't represent the number, it's out of range. And if you want a bigger challenge, add a precise message saying what the loss of precision is between what you can show and what the actual numerical value is. So a few things to do there, but the point of it is, well, partly to get you used to programming, keep you fresh at programming, and also I think by doing it you'll see some of the trade-offs. You'll learn a bit about some of the trade-offs that are inherent in the use of a fixed point binary system. Okay, so next lesson we'll look at floating point, which is what Python uses, and that gives us much more flexibility about the position of the decimal point, because as you know, in Python numbers the decimal point can appear anywhere in the number. Well, that's for next lesson, so bye for now. See you in class.